So thank you very much for the introduction. And also I would like to thank Helena and Alex for inviting me to this perfect workshop. I've enjoyed it very much so far. So today I'm going to tell you something about how we can use all these fancy magnetotransport and thermotransport effects to know something about the structure of the systems that are usually quite stubborn against some exploration, which are antiferromagnets. And in this particular case, I will be talking about the non-collinear antiferromagnets. So basically, those are the people who did all the work. Our excellent PhD students, Josef from Charles University in Prague, who did all the optical experiment, pump probes, and the thermoscanning experiments. Then Freya from Imperial College in London, and she's the grower. She prepared our samples, and she also did all the COMSOL simulations. And Sebastian from TU Dresden, from Helena's group, who made all the, let's call it, global Nernst effect measurements. So I would like to thank those guys, and also Zbigniew for fabricating the devices for our transport measurements. So basically what I'm going to cover today is, I will tell you a little bit about the phenomena that we are using, but you have heard most of this during these last 2 days, so I will just quickly wrap it up. And then I will show you how we can use these phenomena to study mostly the domain structure of our non-collinear antiferromagnet, manganese-3 nickel nitride. And in the end, if time allows, I will tell you a bit about our starting experiments on time-resolved MOOC in the manganese-3 nickel nitride. And basically, most of these results are yet unpublished, so just allow me to not to do many conclusions out of them. I just want to share what we have done so far. So, as discussed several times, just to introduce our non-collinear antiferromagnets, they are really nice, extremely interesting systems because they somehow are halfway between ferromagnets and antiferromagnets. From antiferromagnets, they are usually fully compensated, so they have very small magnetic moment, and they are not very sensitive to external magnetic field. And furthermore, it's predicted that their spin dynamics should also lie in the terahertz region, like for the normal antiferromagnets. And also, which is for us experimentalists particularly important, they cover a wide range of materials. They are isolators, they can be semiconductors, metals, so we have quite a choice here. But from ferromagnets, and this is extremely important for us, they can show certain effects that were thought to be unique only to ferromagnets before, like the Hall effect, Nernst effect, and magneto-optical effect. And this is nice because this gives us a tool to study these systems without that much difficulty, because as you probably know, the collinear antiferromagnets are really hard to study. And so what are these effects? Just to very quickly wrap it up, all of you know what ordinary Hall and ordinary Nernst effect is, that you send either current through a conductive system and apply external magnetic field, and due to the Lorentz force, you get some transverse voltage. The same goes if you, instead of voltage drop or potential drop, you apply a drop of temperature, so thermal gradient, and you get similar effects. Basically, in terms of the symmetry of the measured signal, they are pretty much the same. And also, if we extend this thinking to magneto-optics, you get magneto-optical Faraday effect, and this is, in a way, it's similar because instead of having a voltage, you get an electric field oscillating on optical frequencies, of course, of the electromagnetic field. And after passing through the material with perpendicular magnetic field, you gain, again, transverse, in a way, voltage. You get transverse component to the electric field, which experimentally it shows as a rotation of polarization plane. So this is also gaining some transverse component. So those are just boring, ordinary effects. And if you go to ferromagnets, you get something very similar. Again, for us experimentalists, it's similar. The physics is totally different, and it has been discussed quite extensively. It's related to the periphase curvature, and to there are some intrinsic, extrinsic contributions. But just from the symmetry in ferromagnets, you replace external magnetic field with magnetization, and you get anomalous Hall, anomalous Nernst. And for magneto-optics, it's polar, either Faraday Kerr effect or polar Kerr effect, depending on whether you look in reflection or transmission. Usually these materials are not transparent, so the polar Kerr effect is what you usually observe. And if you have these effects linear in magnetization, you can get the second order effects, quadratic in magnetization, which in transport would be planar Hall effect, or in thermo-transport planar Nernst effect. And those effects are quadratic in magnetization, and they are sensitive to the in-plane component of magnetization. So basically, they all have similar symmetry, and the transverse voltage drop that you measure is proportional to the angle between the current or the thermal gradient and the magnetization. In optics, we have also this kind of fun. It has like 10,000 different names, but usually we call it Voigt effect. But optics, it makes it a little bit more interesting because we have one more degree of freedom in terms of direction of the electric field, which is polarization. So basically this effect is then proportional to the angle between polarization and the magnetization. So this is Voigt effect. So this is, so far, these were ferromagnets. And how is it in the antiferromagnets? So naturally, as you would expect, you can always measure the quadratic effects because antiferromagnet has two sublattices, but these effects do not care about the direction of the magnetic moments, like 180-degree rotation. So even in boring normal collinear antiferromagnets, these effects do not cancel out, and people measured AMR, measured magnetothermal power of planar Nernst, magnetic linear dichroism. This all exists. But these effects are of the second order, so they are small usually. So, but for the normal collinear antiferromagnets, they are the only tool that we have available, so people have studied it quite extensively. On the other hand, it would be nice to have the linear effects. And as there has been mentioned several times during this meeting, there are systems, even with compensated magnetic moments, when the linear effects can occur. Those, in normal standard collinear antiferromagnets, those are prohibited by the PT symmetry. But if this symmetry is broken, and such system exists, then you can observe all these effects, Nernst, Hall, even Moog, and even in the system with no net magnetic moment. And those are particularly those two types of systems. You have heard in the previous talk about the altermagnets, so I'm not going to talk about this one, and let's focus on the non-collinear antiferromagnets. And in this case, you have also like two options. As you have heard, you have can have a coplanar or non-coplanar, and the non-coplanar are the structures with non-zero chirality, where you get all these fancy topological anomalous Nernst, anomalous Hall, and everything. But our system is the coplanar one. And so we will focus on these. This is the system where all the magnetic moments are basically lying in one plane. And due to the triangular structure, in certain groups of symmetry, the PT symmetry is broken, and you can get a non-zero contribution to the Berry phase in K-space, and you get all these kind of effects. So basically, this is also something that has been covered in several talks, the intrinsic contribution to the anomalous velocity and anomalous Hall conductivity is related to the Berry phase curvature in K-space. So there are systems where this is allowed. And so you get a non-zero Hall conductivity. And in non-collinear antiferromagnet, this has been observed in manganese-free tin. Same goes for the Nernst effect. I know, especially in a view of today's talk, that this formula is not totally correct. It's just the standard mod formula that works for ferromagnets that relates the conductivity to, that relates the thermal conductivity to the Hall conductivity to the normal Hall conductivity. But, well, to some extent, it has been calculated that in certain non-collinear systems this works as well, and our system, fortunately, being one of them. So this is how you, if you see Hall effect, you are expected to see Nernst effect, which indeed was measured again on manganese-free tin. And you are also expected to see the Moog, because again, the Moog relates to the conductivity only. In this case, it's a conductivity at optical frequencies. So this means that you have to look particularly well into the band structure because this conductivity is already sensitive to a particular band splittings and particular energy. So this is not as simple as in the case of the normal transport, but still there is certain analogy. And as you can see again on the example of manganese-3 tin, the MOG has indeed been observed. But all these three measurements, all these experiments were done on bulk manganese-3 tin. So what about if we go to different systems and if we go to thin films? And this leads me to I want to show you that even though everything has been basically measured and proved, that there is still new physics and new things to be found in these materials, and particularly with respect to the domain structures. And this is why we focused on the manganese-3 nickel nitride, which is an antiperovskite. It has also this Kagome-type lattice like manganese-3 tin, but in this case it's tilted. It's under a cube diagonal of the cubic lattice. So this is nice because this gives us contributions of both in-plane and out-of-plane components of the lattice. And it has two possible fully compensated magnetic phases, and they are different in terms of symmetry. We call it 5G and 4G phase, which one of them is this kind of like triangular-like lattice, and the other one has different symmetry. And it was also shown that if you apply strain to this kind of structure, you insert a very small magnetic moment. Normally in unstrained structure, it would be fully compensated, but in thin films, this is never the case. So tensile and compressive strain create the opposite sign of this very small magnetic moment, which is indeed like, it doesn't make it ferromagnetic. It's 0.00 Bohr magnetron per unit. So it's like a small moment, but it's there and it enables us to manipulate these systems. Yeah, and just now let me quickly say how these two types of structures differ and why we want one and not the other one. Basically, this is the types of structures that you can have in this material. And this is what we call gamma 5G. This is what we call gamma 4G. And they differ in terms of angle between the cube diagonal and the magnetic moments. So from one case, where this angle is 0, this is this gamma 5G. And the other, where this is 90 degrees, this is this gamma 4G. And if you just look at the symmetry, and I don't have chance to go too much details, but you can check it in this publication. If you look at the symmetry, this kind of structure has 3 Meron planes plus C6 rotation symmetry. And this means that Y and Z components of all these pseudo-vectors, magnetization, Hall conductivity, Nernst-Berry curvature, this is odd, and the X component is even. So if you integrate over the whole brilliance and all possible bands, then you get 0 contribution in the odd component. You just get the X component, but this is 0 as well because of the rotation symmetry. So basically, this phase doesn't give you any signal. On the other hand, this phase, again, you can check the symmetry. Y and Z is even, X component cancels out. And again, from the symmetry, you only get this Z component. So basically, you get anomalous Hall, anomalous Nernst, and MOG. And also, if you add biaxial strain to this, you can have even some small contributions in the 4G phase, in the 5G phase, but this is small. So basically, this system, some time ago already, the anomalous Hall effect was detected, studied thoroughly as a function of the strain, as a function of which it was achieved by adding a different substrate. So it was a growth strain. And it was shown that there is a strong spontaneous anomalous Hall or spontaneous Hall response. And yet there was a very small magnetic moment. So this has been published. And now the question is if we can go kind of beyond and if we can look at the other responses as well. And what is the I think I'm like halfway through already. Still okay. Okay, so we had basically the structures that were the same as for this kind of study, grown by the same group. It was a 20 nanometer thin film, prepared either on STO or MGO substrate at Imperial College, and it was prepared by PLD. And these structures were epitaxial, uniform, And from the magnetometer, it follows that it has a very small spontaneous magnetic moment, like 0.01 Bohr magnetometer per unit, and you see it really drops with temperature, and the null temperature of this structure is around 270 kelvins. So beyond this, it's very magnetic probably, but at low temperature, it's almost fully compensated antiferromagnet. And out of these structures, whole bars were fabricated in Prague with heaters. So whole bar was just E-beam with wet etching, and they added platinum heaters and platinum thermometers so that the Nernst response can be measured. And first experiment that was done by Sebastian in Dresden was this, what we kind of called global Nernst measurement. And basically, they applied current through the heaters, which created a heat gradient in the sample plane and measured transverse and longitudinal voltage. And this was the Nernst signal that was measured as a function of external magnetic field. So this was the Nernst response, and in order to get the Nernst coefficient, it was necessary to calibrate also the thermal gradient, which was done by two different methods, either using the platinum thermometers or simply by using the sample itself. So they measured longitudinal resistance as a function of temperature, and then when they applied the current through the heaters, they measured the change of the longitudinal resistance, which enabled to measure the temperature at different points of the device and thus the thermal gradient. So this was the way how they got a thermal gradient, and so enabled to recalculate the signal to actual Nernst coefficients. And here is a comparison between the obtained Nernst hysteresis loop and the anomalous hole in hysteresis loop. And you see there is pretty good correspondence, both in terms of coercive field, which increases with decreasing temperature, as it should, and also like in terms of the general behavior. But so this is good. This enables to somehow evaluate the Nernst effect in the material. But what needs to be done is to calculate the Nernst conductivity from this Nernst coefficients so that we are able to compare it with other systems. So for this, it basically needed combination of several experiments. It has been derived that the Nernst conductivity is proportional to anomalous hole conductivity Seebeck effect, and then the longitudinal conductivity and Nernst effect. So basically, you need to know all these four values. Those two you get from transport, longitudinal and transverse. And those two you get for the thermo-transport, again, longitudinal for the Seebeck effect and transverse for the Nernst effect. So by this, Sebastian was able to get all these kind of parameters and to roughly evaluate the size of this whole animal's Nernst conductivity. And those are the numbers at different temperature. But surprisingly, we were motivated in thermal study of this material because theoreticians have calculated that the Nernst conductivity should be huge. But in the end, it was not like really huge. It was very surprisingly small, like 3 orders of magnitude smaller than what we have expected from the theory. And also like significantly smaller than what was measured in the manganese free tin. So this was kind of strange, and this is something we don't have proper explanation yet. There are some indication that it might be either the sample, the thin film quality, maybe inhomogeneity of thermal gradient, and possibly, which we have no proof of, the anomalous Nernst coefficient can be somehow anisotropic. So basically what we have is a solid Nernst response, but quite a small one. So the question is, can we use it for something? And we can use it for studying the domain structure of the material. And this was done by using this thermoscanning gradient microscopy, which you probably know. You just scan a laser across the whole cross, and this creates a thermal gradient, and you measure transverse and longitudinal voltage. And you can apply external magnetic field, or you can field cool it to create different types of domain structure. And since the spin structure is along the diagonal, even the out-of-plane thermal gradient can create an Nernst response. So in the previous case, it was the in-plane thermal gradient, and now it's the out-of-plane. And what we found out, that if you do this, if you do the thermal scanning on this type of structure, you get the conventional Nernst signal that Kota was showing on the manganese-3 thin. So this is the conventional, meaning that you measure, you apply out-of-plane thermal gradient, you apply in-plane magnetic field in one direction, like this, and you measure response in the perpendicular direction. So this is what we call conventional Nernst. But there is also an unconventional response, which is in the direction parallel to the external magnetic field. And you see, this unconventional Nernst response allowed us to determine which kind of magnetic domains we are actually having in this type of structure. Because from the conventional, for two directions of external magnetic field, we found out that we get two types of, like two groups of magnetic symmetries. If you apply external magnetic field in this direction, this only allows these types of magnetic domains which have this projection of external of magnetization. So this was only the blue ones were allowed for this type of field cooling. Only the red ones were allowed for the opposite type of field cooling. So that like from all the 8 possible domains that are there, this separated to 2 groups. And the unconventional response allowed us to distinguish which type of groups we are seeing, which type of domains we are seeing in the corner. So basically the red one had a positive Nernst response, those were these ones. And the blue ones had the negative Nernst response, and this was those ones. And we found out that this was of magnetic origin because if we reverse the magnetic field, the color changed. So basically then we got these 2 domains in these corners and these 2 domains in these corners. But the question remained, what was the origin of these domains? And there were several possible mechanisms that could have been involved, some of them being like in-plane thermal gradients or strain in the corners. But gradually we excluded all these mechanisms either by symmetry or by simulation. And what remained was a magnetostatic dipole-dipole interaction that stabilized the kind of macro domains in the corners. So Freya did a COMSOL simulation of this magnetostatic interaction. She added a convolution with the finite Gaussian shape of the beam. And what she got was this type of structure, which resembles quite strongly to what we observed. So our conclusion was that this is really of the magnetostatic origin. And should I end now? Or do I still have time? 2 more minutes. Okay, so then I'll quickly go through the optics. It's really just beginning of experiments, so basically I'll just summarize this. The thing is that these domains make our life a little bit complicated because we, in analogy to the experiment in manganese-3 tin, we tried to observe also the magneto-optical carrier effect in the system. But the problem is that there was like nothing. So the static magneto-optics was not working. But usually, if the static magneto-optics is not working, what you can always do is not to look at the change of the magneto-optical signal, but rather to look at some small changes induced by a strong laser pulse. So we switched to time-resolved magneto-optics. So basically, you have, this is simple pump probe method. You have a strong pump pulse that somehow modifies the magnetic structure, and then you have time-delayed weak probe pulse. So it's kind of this stroboscopic method. And you measure signals as a function of the delay between the pump and probe pulse. So pump excited the system, probe was tuned to, because we knew from theory where the maximum of the magneto-optical response should be, though we didn't see it. We tuned it to this blue region where the maximum should be, and we look at the traces. And indeed, there was a signal, relatively large one, but signal that had a symmetry that is quadratic in magnetization, kind of. So it corresponded, we measured as a function of a polarization plane, and we found out that the symmetry corresponds to the Q-MOG, to the quadratic MOG, which is something that people observed also in manganese-3 tin. But here, what was interesting, that this Q-MOG measurement enabled us also, we saw a shift with external magnetic field. So it enabled us also to see how we are repopulating the domains by adding external magnetic fields. So we saw like a shift that corresponds in normal ferromagnet. This position would correspond to the position of magnetization. In this case, question is what is the magnetization? But anyway, we could see the shift that was present as a function of external magnetic field. But this was nice, but not so much exciting. What was more exciting was the time scale at which this effect occurs. So we checked at the very short time scales of a few picoseconds, and we checked magnetic signal, like meaning the change with magnetic field. And this is not a non-magnetic signal, this is just average over magnetic fields. And especially with this signal, we compared against the change of reflectivity, which reflects somehow carrier dynamics. And we saw that the dynamics was induced on much shorter time scales, like 100 femtosecond perhaps. And this is some hint that maybe the physics is not so simple, that it's not just the demagnetization, as in the case of the manganese retin, but maybe we have some kind of ultra-fast spin torque going on here. So this is now what we are strongly focusing on. So just to quickly wrap it up, we observed anomalous Nernst effect in manganese retin, manganese-3 nickel nitride, sorry, and by two different methods, by thermoscanning and by anomalous, global anomalous Nernst measurement, but we found that response to be relatively small and we don't know why yet. We observed, using this Nernst effect, we observed an unusual behavior of domains in manganese-3 nickel nitride, and using the pump probe methods, we also were able to measure somehow magnetization dynamics in this system, and we still are thinking what this means. And this is it. Thank you for your attention.